In this video, we're going to talk about x as a random variable and the various functions that we define on x. Alright, so given that x is a random variable, we know that it can be discrete or it can be continuous. Discrete or continuous. In either case, we define a probability distribution function, so we denoted f, that takes values from our random variable and maps them to 0, 1. This is called our probability distribution function. And that's true in either the discrete or the continuous case of our random variable. However, in the discrete case, we call it a probability mass function. It is the probability distribution function, but we refer to it as a probability mass function. In the continuous case, we call it a probability density function. They are both probability distribution functions. It's just called something different in the discrete case and something different in the continuous case. Okay, so let's stay on the discrete side for a minute. Oops, let me erase that for now. So what are some things that are true? 1, the probability mass function is greater than or equal to 0 for all values of our random variable. If we sum up all the probability mass function values, we will get 1. And in the discrete case, f of x corresponds to the probability your random variable takes on a particular value x. All right, so the probability mass function is equivalent to the probability that your random variable takes on that value of the argument. All right, in the continuous case, we have that the probability density function is greater than or equal to 0 for all x in a random variable. So remember, in the continuous case, we integrate. In the discrete case, we sum. If we integrate over the reals our probability density function, we will get 1. So those are kind of similar. This time, the probability density function evaluated at a particular value is not the same as the probability. But what we note is that the probability, your random variable, is between, let's say, a and b. That's equal to the integral from a to b of your probability density function. Okay? All right, the next function is the cumulative distribution function. And we have one of those on both continuous and discrete random variables. So we have the discrete case over here, and we have the continuous case. In all cases, if I say, so this is our CDF, and it is a function that goes from our random variable, also goes to 0, 1, but its meaning is different. It's the summing up of probabilities. So we say f of a, or big F of a, is probability your random variable is less than or equal to a. So that's true in both discrete and continuous case. That is our CDF. How we calculate those change depending on if it's discrete or continuous. So over here, if we're going to calculate, in the discrete case, we're calculating big F of a. That means we're going to sum up all of our values of our PMF as long as x is less than or equal to a. So we're summing up all the probabilities up to a. In the continuous case, we integrate from negative infinity up to a, f of t dt, or we could say f of x dx as long as it's not the same as our right endpoint. Okay, so that's our cumulative distribution function. One thing we want to note in the continuous case, that if we know the CDF, if we take its derivative, we get the probability density function. So that's true in the continuous case. All right, let's talk about expected value and variance. So both of those are true in the discrete or the continuous. So mu is interchangeable with the expected value, E of x, and sigma squared is interchangeable for the variance of x. All right, so in the discrete case, so we'll make our columns again, the way we calculate E of x is by summing up all of the x values times their respective probabilities, or in this case, the PMF. Okay, so I could say x in x, so over all x. If we wanted to find E of x squared, we sum up over all x, x squared, f of x. It's very similar in the continuous case. E of x is equal to, instead of a sum, we're going to integrate over the whole reals, x times f of x dx. Similarly, big E of x squared means we're going to sum up or integrate x squared f of x dx. And the reason, remember, that we have this second row is because the variance of x, in all cases, is E of x squared minus E of x squared. That is the mean of the squares minus the square of the means. And the standard deviation of x, which we notate sigma, is just the square root of the variance. All right, lastly, let's talk a little bit about the linearity of the expected value. So if we have the expected value of a linear transformation of a random variable x, we know the constant comes out, and we can pull out the constant plus b. It is not the same for the variance of a linear transformation. It's just a squared times the variance of x. So remember, the plus b has no effect. Now in the case, so we'll say in the case where two random variables, we'll say x and y, are independent, well, then some nice things happen. This is actually true about the expected value regardless of independence, but it's also true if they are independent. So the expected value of the sum of random variables is equal to the sum of the expected values. The expected value of the difference of two random variables is the difference of the expected values. Now here's where independence matters. So in the case where those random variables are independent, then the variance of the sum is equal to the sum of the variance. That's not normally true, or not true when they're not independent. And beware, the variance of the difference is really also the variance of the sum of the variances. Okay? So there's a summary of your functions on a random variable x for both the discrete and the continuous random variables.